Hello again, physics friends. We are back and we are talking about Stern-Gerlach analyzers, and in particular, Stern-Gerlach analyzers rotated to an arbitrary angle. So you'll recall that this apparatus is what we're calling a Stern-Gerlach analyzer. It's basically it consists of a magnet that has an asymmetric or non-uniform magnetic field that's stronger in one region and weaker in the other. And here, where the magnetic field lines that are in dark blue here, where the lines are closer together, that's where the field is the strongest. And when they're further apart, that's where the field is weaker. So we could indicate this field with the following arrow, showing that a north pole of a magnet would be pulled in the upward direction, and the strength of the field is largest at the top and smallest at the bottom. What we see is if we shoot atoms, silver atoms in particular, into this magnet, we're going to get deflections. Now, the classical prediction, as a reminder, is shown in 4. This is the classical prediction, which is that the amount of deflection depends on the projection of the atom's arrow relative to this field direction. And since, in principle, the atoms can emerge from the source with any orientation, we should be able to get any deflection from 0 up to a maximum and down to a negative minimum. But actually, when you do the experiment, you observe 2 dots, and this is the experimental data. And so what this is suggesting is that there's only 2 possible alignments of a silver atom, either aligned with the field or anti-aligned with the field. And this is the quantum reality, that atoms do not behave like arrows pointing in any given direction in space, but there's only 2 possible outcomes. We have a two-state system when it comes to the magnetic alignment of a silver atom relative to a field. Either it's aligned with a field or aligned opposite to the field. So we have this actual experimental apparatus drawn here as a cartoon, but we can represent it schematically because we're not going to draw this apparatus every time we want to draw it on a page. So we can replace this magnet with a series of magnetic arrows indicating the direction of the field and the gradient of the strength of the field. And we can acknowledge that atoms get deflected by the field, and if we'd like, we can then input these kind of redirecting pipes so that at the end of the day, the atoms are now moving horizontally, but they're separated or filtered according to their magnetic alignment. Atoms that are aligned with the field come out the top pipe. Atoms that are aligned opposite the field come out the bottom pipe. So in acknowledgement of that, the fact that the atom is a two-state system, the atom's alignment with the field is a two-state system, we're going to have 1 input and only 2 outputs. And we can simplify this drawing even more with the following symbol. And this is the symbol that we will use going forward. We'll just draw a box with an arrow on it indicating the direction of the field. And we have 2 outputs, aligned with the field, a plus, and an anti-aligned with the field, a minus, and 1 input. So an analyzer, a Stern-Gerlach analyzer that we will call SGA, has 1 input and 2 outputs and a given orientation. One of the big ideas that we want to get across in this video is that we can rotate the Stern-Gerlach analyzer to any arbitrary angle. Okay, so here we're drawing the angle relative to the vertical, and we'll call that theta. So now we have a magnetic field line that's not pointing in the vertical direction. It's pointing off at an angle theta relative to the vertical. So in our schematic representation, we'll draw the diagrams in the following way with a box that's rotated away from the vertical by an angle theta. And since we can orient this Stern-Gerlach analyzer in any direction, we want to make sure we have a defined coordinate system so that we can talk about the orientation of this device. And so we're going to use a Cartesian coordinate system, x, y, and z. And y is going to be the direction that the input atoms are moving. So the atoms are going to come in moving in the y direction, and they will exit moving in the y direction. So when we rotate this device, we are rotating it in the xz plane. Okay, so as drawn here, the vertical is the z direction, and that corresponds to theta equals 0. If you rotated by 90 degrees, then your box would be aligned in the x direction, And if you rotated by some angle that was in between 0 and 90, then it would be represented by this dashed line here, angle theta away from vertical or away from the z-axis. So we are going to label a Stern-Gerlach analyzer with a subscript, and that subscript indicates the orientation. So we could have an SGA Z if it was aligned with the z-axis. We could have an SGA X if it was aligned with the x-axis. And we could have an SGA theta if it's at some other angle relative to this coordinate system. And we're going to label the outputs of our analyzer with the following in the following way, right? So this box is making a measurement of the quantity m theta, which you can think of as the orientation of the magnetic property or the magnetic alignment of the atom in the theta direction. And there's only two possibilities. Either it points parallel to that direction or it points anti-parallel to that direction. So we'll say that we're measuring SGA theta and we get a value of either plus MB or minus MB. And you'll recall that this term MB is simply a numerical number. You can think of it loosely as +1 or -1. For our purposes, the exact value of that term MB is not going to be important at all. You'll also remember that there's kind of a pairing between our cartoon description of color and hardness and the actual properties of MZ and MX. So MZ and MX are two measurable properties of the silver atom, and they are incompatible observables in the same way that we said color and hardness were. So if you think of a color box as SGA-Z, then the hardness box could be an SGA-X. And all of the experiments that we did with color and hardness will have the same outcomes if you replace color and hardness with SGA-Z and SGA-X. The other thing to point out is that an SGA-Z is nothing more than an SGA theta with theta is equal to 0. Because when theta is equal to 0, then the orientation of the analyzer is parallel to the z-axis. And similarly, an SGA in the x direction is nothing more than an SGA 90 degrees. In other words, theta is 90 degrees, corresponds to the situation where the magnetic field on the Stern-Gerlach analyzer points in the x direction. So we should just think of SGA theta as any arbitrary orientation, and we'll sometimes use SGA-Z for theta of 0 and SGA-X for theta of 90. And so we can now see a distinction between color hardness and Stern-Gerlach analyzers. Color and hardness, you can't make any adjustments to them. It's just a color box and a hardness box. But with the Stern-Gerlach analyzer, there's more than two options for the alignment. You could have it in the z direction, x direction, or any angle, theta going from 0 to 360. And so we have more options for Stern-Gerlach analyzers than we do for color and hardness. Okay, so it turns out that this color and hardness analogy holds for any two Stern-Gerlach analyzers that are perpendicular to each other. So z and x works, minus z and minus x would work, plus and minus 45 degrees would work. Any pair of analyzers that are 90 degrees would have the same exact properties as a color hardness pair in terms of the transmission probabilities and so on. But because we're allowed to put the SGA, the analyzer, at any arbitrary angle, we have to be a little bit careful and have a more mathematically complete way of describing the transmission probabilities. Because let's say, for example, we had an SGA 0, so that would be a Stern-Gerlach analyzer aligned in the z direction. And then we tacked onto it a Stern-Gerlach analyzer that's tipped but only a little bit away from vertical. Okay, so we could call this an SGA 5 degrees or something like that. Okay, so this angle might be only 5 degrees or so. Okay. Well, this outcome would not be the same as color hardness. In other words, with color and hardness, if you had a color box followed by a hardness box, the exit probabilities of the hardness box would be 50-50. But here it doesn't seem right that if we take a plus MB in the z direction and we feed it into an analyzer that's very closely aligned with the first one, that we would get 50-50 probabilities at the output. And indeed, that would not happen. We would be much more likely to exit the plus port, high probability, and low probability of exiting the minus port. Okay. And so we need a way to quantify this. Like, what does high probability mean and what does low probability mean? What is the mathematical description of the probability of transmission as a function of the angle between the two analyzers? We know that at 90 degrees, those probabilities end up being 50-50, but they're not going to be 50-50 if the angle between the two analyzers is only 5 degrees. So let's see what that actual value is. So here we have the setup that we're going to focus on. And we can call this experiment 4.4 to align with what we have in our class notes. The experiment is start with a measurement or with an analyzer that is oriented in the z direction, and then follow it up with an analyzer that's oriented in an arbitrary direction theta. So we're not going to give it a number, or we're not going to say 10 degrees or 5 degrees. We'll just leave it symbolically as theta. Then notice we send in some input atoms in an undefined state. Okay, and this first analyzer basically prepares all of those atoms so that the ones we send into the subsequent analyzer are all mz equals plus mb. So every single one of the atoms that goes into the second analyzer is plus in the z direction. Okay, we're just going to ignore the atoms that come out of the minus port of the first analyzer. The question then is, what fraction of these input atoms to the second analyzer come out of the second analyzer's plus port? Okay, and we know a little bit about, we know some constraints on this, right? We know that if theta is 0, the probability of exiting the second analyzer is going to be 100%, because that would be an SGA z followed by an SGA z, and it's a repeated measurement of the same property, so we've got to get plus again with 100% probability. And we also know that if theta is equal to 90 degrees, the probability will be 50-50. It's like a SGA z followed by an SGA x, which is very much like a color box followed by a hardness box, or vice versa. We're going to have a 50-50 chance. The other thing we know is if theta is 180 degrees, the probability will be 0. Okay, that's like an SGA z followed by an SGA in the minus z direction. Well, if you came out of the plus port of a z analyzer, then your arrow is pointing up on the page. So you got to come out of the minus port of a minus z analyzer. So whatever mathematical function we're going to have has to satisfy at least these three properties, that at these three angles, theta of 0, theta 90, and theta 180, we get 100%, 50%, and 0% transmission. So I'll show you a graph of the actual exit probabilities that are determined experimentally. Here we go. And notice that this probability has all of the features that we asked for and we care about. When the angle is 0, the probability is 1. When the angle is 90 degrees, the probability is 1/2. And when the angle is 180, the probability is 0. And it's a periodic function. What that means is if you cycle through from 0 to 360 and then you come back again to 0, you better repeat the probability. So you can rotate this analyzer over and over and over and over again, and every time you come back to the same orientation, you better get the same probability. So that's saying your function is going to be periodic and returning to the same point each cycle. And it's smoothly varying, so the probability starts at 100% and drops down to 0 and rises back up to 100% and would drop down to 0 again. And there's a mathematical equation that describes this, and that equation is the cosine squared of theta over 2. So you take the angle, divide it by 2, compute the cosine of it, and square the result. So for example, let's look at 45 degrees. We would have a probability of cosine squared, let's look at 90 degrees. at 90 degrees, we would have the cosine squared of 90 degrees over 2, which is the cosine squared of 45 degrees, which is cosine of 45 is 1 over root 2. But we are squaring that thing, and we end up with 1/2, which is exactly what we see on the graph, and also what we knew had to be true based on previous experience. So this is the function that describes the probability of going from a plus port to a plus port. So we might call this the probability of plus to plus is given by cosine squared of theta over 2. Incidentally, we can build up some intuition for this cosine squared theta over 2 equation in the following way. Given that we know that we want the probability to be 100% at theta equals 0, so we know that at theta equals 0, we need 100% transmission probability. We might start out by thinking maybe the probability would be given by cosine. Okay. And so you could make that plot, and cosine does indeed start at 1 at theta of 0, but the problem with cosine is it goes negative, and we don't have negative probabilities, so that's not going to work so well. So the next thing you might try is, well, let's just take that graph and shift it upwards, okay? So instead of letting this graph go negative, I will shift it up by 1, and I'm going to shift it up by 1 because the most negative value I have is -1. So if I add 1 to it, it becomes 0. So everything will be positive. So if I plot cosine of theta plus 1, then where I used to be at -1, I'm now going to be at 0. The problem, though, is that where I was at 1, I'm now going to be at 2. And my function is a vertically shifted cosine that goes from 0 all the way up to 2. Okay. So that's no good because I can't have a probability bigger than 1 or 100%. So then I'm going to divide by 2. And when I do that, I have cosine theta plus 1 all divided by 2. That is now going to go from 1 down to 0 and ramp up to 1 again. So this has all the properties that we want, right? It never goes negative. It's always between 0 and 1. And it's periodic and smoothly varying. And in fact, what you can show is that the cosine of theta plus 1 over 2 is exactly cosine squared of theta over 2. There's trig identities that can get you from the left side to the right side. In case you're curious, here's the trig identity that the cosine of the double angle is equal to the difference of the squares of cosine of that angle and sine squared of that angle. So we could say cosine of theta is equal to cosine squared of theta over 2 minus sine squared of theta over 2. And we can use the fact that sine squared of anything plus cosine squared of that same thing always adds up to 1, a fact that we'll come back to in a little bit. So instead of minus sine squared theta over 2, we can replace that with cosines. So we could say minus 1 minus cosine squared theta over 2, which we can then write as 2 cosine squared theta over 2 plus minus 1 is equal to cosine of theta. And if we simplify this or rearrange this, we get cos theta plus 1 divided by 2 is cosine squared of theta over 2. Yay for trig identities. Incidentally, we now know that the probability of going from the plus port of an analyzer to the plus port of a second analyzer depends on the cosine squared of the half angle between those two analyzers. But what about the probability of going from the plus port of the first to the minus port of the second? How do we figure that one out? And that, again, we can use some trig identities for because we know that an atom has to come out somewhere. So atom must come out of the plus or minus port. It can't just get stuck in the analyzer. It's got to come out somewhere. So that means 100% of the atoms will exit. So we know that if we add up the two probabilities, the plus plus and the plus minus, we better get 100%. Or another way to say it is, if we use non-percent values like 1, then those two have to add up to 100%. Well, we know that the plus plus probability is cosine squared theta over 2. So we can solve for the plus to minus probability, and that's 1 minus cosine squared of theta over 2. But again, remember that if you have sine squared of something plus cosine squared of something, you're going to get 1 always. So 1 minus the cosine squared of an angle is equal to the sine squared of that angle. So we can replace this term with sine squared of theta over 2. So the probability of exiting the minus port of the second analyzer is simply sine squared. So we can add that in here. And now we're guaranteed that the atom's going to come out somewhere, because mathematically these two probabilities will always add to 1. And the cosine squared and the sine squared are kind of complementary to each other, right? So if we have a plot of cosine squared, it looks like this. And a plot of sine squared would start at 0, ramp up to 100%, and then ramp back down to 0, like so. Okay, so this gives you some idea of how to compute probabilities coming out of a Stern-Gerlach analyzer at an arbitrary angle. So I'll put up these main takeaways, at least from my point of view, right? The silver atom's magnetic orientation can only have two values. It's a two-state system. Either it's aligned with a field or it's anti-aligned with the field. Okay, and the orientation is only defined in one axis at a time. So if you measure the orientation in one axis, then it has no defined orientation along any other axis. That said, you can compute the probabilities of being up or down in any other direction, but you can't say for certain whether it's up or down in that direction. Given that an atom has exited the plus port of the first SGA, then the probability that it will enter the plus port of the next SGA is given by cosine squared of the half angle. And again, if theta is small, meaning the two analyzers are pretty well aligned, then you're going to have a high probability of getting plus again. And if they're at 90 degrees to each other, then your probabilities become 50-50. The other item that I want to make sure you guys are clear on is only the relative orientation of two SGAs matter. Okay, so the probabilities for an orientation that's like SGA Z, then SGA X, those exit probabilities are the same as SGA 45 going to SGA minus 45, because those two analyzers are also 90 degrees apart. And it would be the same for SGA of 10 degrees going into an SGA of 100 degrees. Those two analyzers are also 90 degrees apart. Okay, well, we had a nice chance to take a tour through tilted SGA land. And next, we're going to talk about Stern-Gerlach interferometers and what it means to make a measurement versus not making a measurement, even if there's a magnetic field present. Until next time, take care and be well.